Welcome back to our second topic in AP Calculus BC. This topic focuses on series convergence tests, and that's kind of a weird title because we haven't talked about any of those so far. We haven't defined a series, we don't know what a convergence test is, and in fact, we still have a few days before we get to convergence tests. However, today we are finally going to define a series, and in particular an infinite series, and start to march closer to our final goal of these convergence tests of our series. So we're going to go ahead and start with the sequence a sub n equals 0.9, 0.09, 0.009, and so on and so forth. Or maybe I should say the right way, 9 tenths, 9 hundredths, 9 thousandths, and 9 ten thousandths. So the first thing we're going to try to do is identify the type of sequence. So is it going to be geometric or like exponential? Is it going to be arithmetic or like linear, quadratic, something like that? Yeah, so either way. And then 2, you're going to write that general term. 3, you're going to start to find those partial sums. And then we talked about partial sums last class, I think. And then 4, you're going to find the limit of the value of those partial sums. So go ahead and pause me, try those 4, they're nothing too terrible, and then unpause whenever you're ready. Alright, type of sequence. Well, I'm actually going to write this using fractions. I think it might be a little bit easier. We have 9 tenths, 9 hundredths, 9 thousandths, and 9 ten thousandths. And then there is a ... Okay. Well, I think if we treat this, and I'll look at the general term over here, I think if we treat this as 2 completely separate patterns, then the pattern on the top is really easy. The pattern on the top is just 9, no matter what a sub n is. And then the pattern on the bottom isn't too terrible. I think the pattern on the bottom is multiplying by 10 every time. So to me, that seems like it's exponential or geometric, whatever you'd like to call it. So I know it's going to be 10 to the nth power, and let's just see if I'm right. I mean, if I replace n with 1, do I get the first term? And I think I do. Replace n with 2, yeah, I think we're doing just fine here. So 9 divided by 10 to the nth power. All right, now let's find these partial sums. Partial sums can be a little bit tricky here, but it's not too bad, especially I think if you go the way that I explain it to you. So, of course, my first partial sum I didn't write here because my first partial sum means just take the first term, and the first term is 9 tenths. Well, to find the second partial sum, what it really means is add up the first 2 terms. So the first term is 9 tenths, and then, of course, the second term in our pattern over here is 9 one hundredths. And then I think we probably need some like terms here. So we have, looks like, I think we'll have to multiply this by 10, won't we, to get 90 one hundredths plus 9 one hundredths. And I'm looking at 99 one hundredths. Okay. Well, S sub 3 then is going to be the first term plus the second term plus the third term. But notice that we've already added up the first 2 terms. So really all S3 is going to be is the second partial sum, which is 99 one hundredths, plus the third term, right? Plus 9 one thousandths. So really we're just looking at 99 one hundredths here plus 9 one thousandths. And again, I think we'll have to multiply that second one by this first one by 10 here. And then we give a common denominator, and it looks like we get 999 divided by 1,000. My guess is that you can actually already see the pattern here. You could probably go through and figure out what S sub 4 is. I'm pretty confident it's going to be 9999, 9,999 ten thousandths. Right? Just based on this pattern every single time. Now, if we can write a pattern for this then what we could really do is we could actually write a formula, a general term for S sub n. And my general term then is going to be created by looking, and I'll highlight this over here, let's do maybe purple. We're going to look at these 4 numbers at the end and treat them like a sequence. Well, how does this sequence work? Well, the denominator is multiplying by 10 every time, right? 10, 100, 1,000, something like that. I think the denominator is going to be 10 to the nth power. That didn't change. However, the numerator is a little different. It becomes 9, then 99, then 999. You're like, but that's a really weird pattern. You're not multiplying, you're not adding anything. But for this once, look at the relationship of the numerator to the denominator. Isn't it just one smaller than the denominator every time? So couldn't we say that it is the denominator, but just one smaller? And then we might get there. I think this is actually going to give us a formula that will tell us any partial sum number we want, right? If I replace n with 5, then we can replace the n's in here with 5, and that's going to give us the sum of the first 5 partial sums. And then if I wanted to take the limit of this, well, the limit of this guy, and we'll show maybe 2 steps here. The limit is n approaches infinity of 10 to the nth minus 1 divided by 10 to the nth. And that looks kind of intimidating until you remember dominance. And at infinity, subtracting 1 from an infinitely large number effectively does nothing. So we really just treat it as 10 to the nth divided by 10 to the nth. And of course, anything divided by itself is 1, and the limit of a constant is just a constant. And so we end up with 1. All right, let's get to it. An infinite series is the sum of an infinite set of numbers. Usually it's the sum of an infinite sequence. So a sequence is just that pattern of numbers. A series is when you sum them up. And you learn about series later on, especially actually you learn about them in physics, you learn about series circuits, and it's really just summing up things. So you need to get used to seeing series and think sum. But it's also kind of confusing because then you get that sequence word in there, and a sequence isn't a sum, it's just the actual original pattern. We usually discuss sequences in terms of a sub n, lowercase a, and we write them as individual terms. Well then, s sub n, which is going to be the infinite sum of the sequence a sub n, is given like such. We could say s sub 1, our first partial sum, is just the first term of the sequence. S sub 2 is the first 2 terms added together. S sub 3 is the series of the first 3 terms. And s sub n, where n is where we want to stop, could be shown by adding up like this. Or, of course, we could even write this with summations, right? Where we could say we're summing from 1 to n, but n is, of course, infinitely large, and this is a nice way to write it, though the more succinct way to write it is to just put the infinity on top. Kind of an abusive notation because infinity is not really a number, but we really, I assume, know that if someone puts an infinity up here, that this is what they mean. Now, it does become fairly tedious to sum up an infinite number of terms. So if I asked you to find the infinite series of an infinite sequence, you probably wouldn't want to do 1 plus 3 plus 5 plus 7, so on and so forth. There are many terms. There's an infinite number. So instead, we try to do what we did in the opener. We try to identify a pattern in the partial sums, right? And that's what we did up above. But let's look at one more. So just going through this again, let's go ahead and find each of these partial sums. And full disclosure, before I find the partial sums, I always find up to this term number and list it out because I just find it easier for me. So what I'm going to do here is actually list the first 4 terms. And you might need a little extra space here, but my first term, and let's be a little bit more clear too. I'm going to look at the sequence here. And the sequence's general term is 1 divided by, I used n here, so I'm going to just switch this to n's. I like writing n's more than k's anyways, so This is the general term for my sequence. When we put the summation in front of it, that's what makes it a series. So before I start finding these partial sums, I'm just going to look at the sequence all by itself. And I'm going to find the first term of the sequence, and that's just found by replacing n with 1. And we can show the math here. It's nothing too bad, right? 1 divided by 1 times 1 plus 1. That's 1 times 2. That's 1/2. My second term in the sequence is 1 divided by 2 times 2 plus 1. That's 2 times 3. That's 1/6. My third term is going to be 1 divided by 3 times 3 plus 1. 3 times 4 is 12. And my fourth term is going to be 1 divided by 4 times 4 plus 1. 4 times 5 is 20. Okay? So we are going to use those terms and start to calculate partial sums. So first partial sum, super easy. It's just the first term. Just means add up to the first term. I can do that. S sub 2, though, is a little trickier. take the first term, we have to add all the way up until we get to the second term. The second term is 1/6. We do have some fractions today. You're definitely be good with those common denominators. I mean, hopefully you already are, but either way, so multiplying by 3, and then we get 4/6, and I'll even reduce here. And sometimes the pattern's easy to see with the unreduced fraction form. Other times it's easier to see with the reduced form. So I get 2/3. Okay, S sub 3, again, you could do 1/2, right, plus 1/6, plus the third term, which is 1/12. But we already know the answer to this first part, right? This answer to the first part is over here. That's 2/3. So then we're just adding 2/3 to 1/12. And I might run out of room here, sorry. Common denominators, we need to multiply by 4, so 8/12 plus 1/12 gives us 9/12. And then if we reduce 9/12 dividing by 3, I think we end up getting 3/4. Okay. And then let's look at one more, S sub 4. Well, we can be a little more efficient. We know it's going to be 3/4 because that is the sum from the first 3 terms plus the fourth term, which is hanging out over here. That's 1/20. Okay, I think we'll need some common denominators here, multiplying by 5, 15/20 plus 1/20, 20th, not 12th. Numbers are hard. So we end up with 16/20, and then divide by 4, we end up with 4/5. Okay, now, let's go ahead and see if we can figure out a pattern in these partial sums. And honestly, I like to go through and just write out the first couple partial sums. We got 1/2, and then 2/3, and then 3/4, and then 4/5. And really, we could go on forever, but we just found the first 4. Now, a couple things to look at for this pattern. First, is there a pattern? And I think it is pretty apparent that there's a pattern. The 2 goes here, the 3 goes here, the 4 goes here. And so really, each fraction just is increasing the numerator by 1, increasing the denominator by 1. And you could go ahead and put that in words, right? So if you thought about it as a fraction, right, we increase the numerator by 1, and same thing, you also increase the denominator by 1. And those are supposed to be little air quotes, but that's okay. Nice. Now, how do we find the pattern in these partial sums? Well, this is what we've practiced the last couple days, so hopefully we're getting pretty good at it now. We're going to need that fraction line. Okay, let's look at the pattern on the top. It looks like you're adding 1 every time, so we know the slope is 1n. And then we check. We say, well, if n is 1, will it equal the top term? And yeah, it actually will. So I think the formula for the top is just, for the numerator, is just 1n. Let's look at the denominator. Looks like we add 1 every time, so I know again it's going to be a slope of 1. And then we see if we got it right. If we replace n with 1, do we get 2? And no, we don't. We are 1 short of it, so I think we need to add an extra 1 here. So if we wanted to find the sum of the first 6 terms then, right, that's called S sub 6. Instead of going through this whole fraction, adding everything together, now we have a formula for the sum of the first 6 terms. It just becomes 6 divided by 6 plus 1, which is going to be 6/7. That's very cool, right? So we extended our use of patterns with sequences into series, and the way we did that is we actually did have to add up a few terms of the sequence first, but then once we finished adding all of those up, we were able to find a pattern, and then once we had a pattern, we could write a general term for the sum, and notice we used a capital letter for the sum. That's very common, and then we could sum everything up from there. Hooray! All right. There are really 6 of these problems for you, and your goal is to really do exactly what we just did above. However, we're going to go one step further. And the one step further is we're going to go through and actually find the sum of this infinite series, right? We are adding up every single one of these, and we're seeing to what will this add up to. Well, first you added up to 0.5, and then it became 0.66, and then 0.75, and then 0.8. It's adding up, but it's slowing down a bit. Well, how do we actually find the overall sum? Well, that's actually what we did up above in the opener as well. We are going to take this general term and say, well, we plugged in 6 here to find the sum after the first 6 terms. Let's go ahead and find the sum after an infinite number of terms, right? Which is really saying all the terms. Now, we don't actually use that notation. We use the limit as n approaches infinity of s of n. So we need to take the limit as n approaches infinity of n over n plus 1, our general term for the sums. Okay, and then use dominance. We'll pretty much follow this every time. N divided by n, anything divided by itself is 1. Which tells us, and this is actually a pretty interesting idea, that if we were able to add up every single term in that infinite sequence, the final result would be 1. So that's all you're going to focus on for these 3 over here, or for these 6 over here. Your goal is to find the first 4 partial sums, and honestly, I would say even before you start that, you might want to actually find the first 4 terms just to make your life a little bit easier, right? First 4 terms, see what you get. Then start finding the partial sums with those terms. Hopefully you're going to be able to see a pattern in those partial sums, so you're going to identify a formula for the general term. And then last but not least, you are going to find the value of the infinite series, and that value is where you do the limit as n approaches infinity of your general term for the series. If you get stuck on any of these, you are definitely welcome to check my answer key. I have one at the end. Look how I showed everything out, right? I showed your first 4 terms. I showed the math to find the sum of the series. I showed you the general term, how I got there, all that fun stuff. At the very end, it's going to ask you if there are any series for which you couldn't find the sum. And then it's going to ask you, why couldn't you find it? Did you struggle identifying a pattern? Didn't know how to do the limit? Something like that. And there are going to be at least 1 or 2 of these where even though you can find the original terms, you can find the sum of the terms, you may struggle to see that pattern. So you should definitely check my answers at the end. I wish you the best. If you do have any questions, please feel free to contact me. Definitely check your answers when you finish, because I left you a couple notes, especially on this last part that you should read. Good luck.